All right, so part 2 of 14.1. All right, so just a recap of our results from yesterday. So if we have a region in the plane and it's bounded by above and below, the boundary of our region is a function of x. We decided we could find the area of this region by setting up a vertical rectangles, and we can represent the area was this iterated integral from a to b, integral from f1 of x, f2 of x, dy dx. And if our region was bounded on the left and right, the boundary of the region were functions of y, we just switch the order of integration and we set up our iterated integral the opposite order. And for this one, we set our rectangles horizontal, and we sum the area of those little rectangles. Find the area of one rectangle, and then we sum the rectangles through the region. For that one, we said the area was the integral from c to d, integral from g1 of y, g2 of y, dx, dy. And we call this type of region horizontal or vertically simple. And this one horizontally simple. And the way I usually refer to it is just we're going to set our rectangles vertically or set them horizontally to do our integrals. But you will hear the term vertically simple and horizontally simple. You might see it in the book. So what I want to do today is, so yesterday we were just practicing evaluating these iterated integrals. I want to do some examples of setting up iterated integrals to find the area of a region in the plane. So set them up and then talk about how we're going to change the order of integration and why we might want to do that. So that's what we're doing today. So just extending what we did yesterday just a little bit. Is everybody good with this concept so far? Okay. So let's find the area with an iterated integral. So we're going to start just by having the graph given to us. And then we will do some where we actually have to sketch the region and come up with our boundaries. This is y equals 1 over the square root of x minus 1. And we're going from 2 to 5. And we know how to set this up from calculus 1, but we want to write and evaluate an iterated integral for this area. So for this particular example, are we going to set our rectangles vertically or horizontally? Vertically. I find it helpful to draw the little rectangle in there just to remind me. When the regions get more complicated, it definitely helps to visualize. So we're going to do vertical rectangles. And it can also be helpful to label your limits of integration. So for my inner integral, we're going to say that y is going from 0 to 1 over the square root of x minus 1. And for the outer integral, x is going from 2 to 5 dy dx. And that would be our iterated integral. And now we want to evaluate this. So when we evaluate this inner integral, the integral with respect to y, what do we end up with? Integral of dy is just y, and we're evaluating y from 0 to 1 over the square root of x minus 1. We just end up with 1 over square root of x minus 1 dx. And then we're going to evaluate this integral. So how are we going to evaluate this one? This one should be easy. U equals x minus 1. Du equals dx. So we have the 1 over the square root of u du. So that's going to evaluate to 2 square root of x minus 1, and we're evaluating from 2 to 5. And that evaluates to 2. So I'll do it on this one just so we know. We're going to be doing a lot of integrals from here on out. And to do the examples, I will not be able to go through every single step of evaluating integrals. So we'll be doing a lot of things like this, where I say this is how it evaluates, and it evaluates to this. So you may need to go back and fill in those steps on your own, just because we end up doing a lot. I'll do it here. So we end up with, if u is square root of x minus, u is x minus 1, we have the integral of du over square root of u. And when we integrate this, we get, so when we're integrating u to the minus 1/2, so when we integrate u to the minus 1/2, what do we end up with? U to the 1/2 over 2. And we have 2 of those. Oh, wait, we have u to the 1/2 over 2? 2 u to the 1/2, right? There we go. That's where the 2 comes from. So we have that 2 to get rid of the 1/2 when we take the derivative. So this evaluates to 2 square root of x minus 1, but from 2 to 5, and when we evaluate that, we get 2. So that one's a pretty easy example. All right, questions there? All right, let's look at another one. So here's our region for this example. And this is x squared plus y squared equals 4. And we want the area of that region. So are we going to do our rectangles vertical or horizontal here? Does it matter? Doesn't matter. If we have a choice, I usually choose vertical rectangles, just my personal preference. So I'm going to set my rectangles this way. and that's going to be my dx. So my boundaries, my boundaries on x are going to be from 0 to what here? 0 to 2. And y is the square root of 4 minus x squared. So when we set up our integral, we get our integrals. We get the integral from 0 to 2. The integral from y varies from 0 to square root of 4 minus x squared. dy dx. And when we evaluate that first integral, we just end up with y. We're evaluating y from 0 to square root of 4 minus x squared. So we end up with 0 to 2, square root of 4 minus x squared dx. What do we have to do here to evaluate this integral? This is going to be a trig sub. When we, what we will do eventually, in not too long, we will talk about evaluating these double integrals in polar coordinates, and this one will be much easier in polar coordinates. But we're going to do this in rectangular coordinates for now. It's a circle, right? So if we set it up in polar coordinates, it turns out pretty nice. But here's our trig sub. Here's how I set it up. This is x. This is 2 square root of 4 minus x squared. And what did you just say, Dylan?
Well, we know it's a quarter of a circle and we know the radius.
Right, we know it's a quarter of a circle, we know it's the radius. So we should be able to, hopefully we get to the right answer and we'll be able to check, right? So we're finding the area of a quarter of a circle the hard way, really. So for my trig sub, this is how I set up my triangle. So this gives me cosine theta is the square root of 4 minus x squared over 2. And we get, I'm just going to write my sine theta is x over 2. So x is 2 sine theta to find my dx. So dx is 2 cosine theta d theta. So what we have in the integral, I'm going to leave the limits off for now until we evaluate this. So we have the integral of 2 cosine theta, that's our 4 minus square root of 4 minus x squared, times dx, which is another 2 cosine theta d theta. So we end up with 4 cosine squared theta d theta. Do we remember how we evaluate, what we want to do to evaluate cosine squared theta d theta? We have an identity. This identity from here on out, this identity comes up a lot. Anytime we're evaluating an integral that has trig functions in it, we may end up using this identity. Cosine squared theta is 1 plus 2 cosine theta over 2. Sorry, cosine 2 theta. This identity is going to come up a lot for the rest of the semester. So we're going to use that identity. So we get 4 integral of 1 plus cosine 2 theta over 2 d theta. We can cancel out this 2. We end up evaluating 1 plus cosine 2 theta d theta. So we get, when we evaluate that, 2 theta plus sine 2 theta over 2. And now we need to find our limits. So we're going from x equals 0 to 2. And x equals 2 sine theta. So at x equals 0, theta equals 0. I'm using this to find my theta values when x equals 0, theta equals 0, and when x equals 2, I get sine theta equals 1. X was 2 sine theta. So I was making sure 2 sine theta from here. X equals 2 sine theta. So when x equals 0, theta is 0, and x equals 2, sine theta equals 1. So theta equals pi over 2. So we're evaluating this from 0 to pi over 2, and that evaluates to pi. And did we get the right answer, Dylan? 1/4 of pi r squared should be. All right, questions there? So these are pretty easy examples, and we're doing basically we're adding a step to what we did in calculus 1 to find the area of this region using an integral. We're just adding that separate integral. What we're going to do eventually is we're going to add some other things inside the integral to find different quantities. Let's look at an example where we have to be careful with how we need to make some choices about how we set up our rectangles. For this one, we could do it either way. Sometimes it makes more sense to do it one way or the other. And for this one, we need to find our limits of integration. So the boundary of our region are the functions y equals x, y equals 2x, and x equals 2. So we want to find the area in the plane bounded by these functions. So the first thing we want to do here is make a sketch. And it's always helpful if they don't give you the region to sketch the region. So here's y equals x. Here's y equals 2x. And here is x equals 2. All right, so for this region, are we going to want to set our rectangles vertically or horizontally? If we set them, I would choose vertical, because if we set them horizontally, in this area, we're evaluating between y equals 2x and y equals x. And then when we get to here, we would have to evaluate from between y equals 2x and x equals 2. So we would have to set up two separate iterated integrals. So I'm going to set up my rectangles vertically, and then through the whole region, y is varying from x to 2x. So I can just set up one iterated integral. So I'm going to set vertical rectangles. So our area is going to be, x is going to vary from 0 to 2. Y is going to vary from x to 2x. dy dx. And this one should be an easy integral to evaluate. 0 to 2, when we evaluate this integral, y from x to 2x, we get 2x minus x, just like we would do when we set it up in Calc 1 dx. And that's an easy integral to evaluate. When we evaluate that, we end up with the area being 2 units. Is there an easier way we could find the area of this region without doing integrals? It's a triangle. The base of the triangle, we could figure out the length of the base of the triangle. and the height of the triangle is 2 units. So what was it, 2 years ago? I had a student that would, in this type of situation, he'd say, let's use geometry. Rather than calculus, use geometry. What's the easy way to do this problem? He'd say, use geometry. All right, questions there? All right, so we can always set up our iterated integrals using either order of integration. Often, in this situation, one orientation will be easier for our rectangles. Often, one orientation will make the integral possible to evaluate. A different orientation of your rectangles could make your integral impossible to evaluate, depending on the functions. So let's take a look at, if we're given an integral set up in a certain way, how we switch the order of integration. So we want to switch the order of integration. All right, so for this particular example, we want to sketch the region and switch the order of integration. So our integrals that we're given are iterated integrals, 0 to 9. Square root of x to 3, dy dx. So the first thing we want to do is sketch our region. The limits of integration tell us our region. So our limits of integration, we're doing dy first. The limits of integration say that square root of x is less than or equal to y, less than or equal to 3. That's what this inner integral is telling us for a region of integration. And the outer integral says that 0 less than or equal to x, less than or equal to 9. So this tells us how we're going to sketch our region. So here's my xy plane. Our sketch doesn't have to be beautiful and perfect. It just has to give us a decent idea of our region. So y is going to go from the square root of x to 3. Well, here's y equals square root of x. And here's y equals 3. And here is x equals 9. So in my sketch here is the region above or below square root of x, y equals square root of x. Y goes from the square root of x to 3. So that tells me my rectangles are here. Y varies from the square root of x to 3, and x varies from 0 to 9. So this would be my region. So now we want to switch the order of integration. So we want to set our rectangles. We want to set our rectangles horizontal. So if we set up our integral, x here is going to be our inner integral now. X is going to vary from what to what in this region? 0 to, and I need to rewrite this as a function of y. So x equals y squared. So x, if I set my rectangles horizontally, x is varying from 0 to y squared. And y is varying in this region from 0 to 3. So if I switch my order of integration, this would be my iterated integral. X is varying from 0 to y squared, and y is varying from 0 to 3. So the mistake that students often make when they're switching order of integration is they just turn everything around, put them in a different order. You have to sketch the region, and you have to find your limits of integration from the region when we switch the order of integration. All right, questions on what we did there? So for this particular example, switching the order of integration, it doesn't really matter what order we do it in. Either one of these integrals is fine to evaluate. I kind of like the way this one looks better because we don't have the square root of x, but that one's not a tough one to evaluate. All right, so let's look at one where it does matter. So we're going to do the same thing for this example. We want to sketch the region and then evaluate the integral. So our integral is from 0 to 2, and then from x to 2, e to the minus y squared dy dx. So first off, before we even sketch this, is this going to be a vertically simple region or a horizontally simple region in the order that we have it written? What is it? Vertically simple, because we're evaluating y first, so y is varying from x to 2. So we have our rectangle set vertically. To evaluate this integral, we would have to evaluate e to the minus y squared dy. Do we know how to evaluate that? That one is a very tough one to evaluate. So the integral of e to the minus y squared dy is difficult. We don't have a du to do a u substitution. This is going to be a difficult integral. So let's sketch the region and switch the order of integration, see if that helps us simplify this integral. So here's my region. X is varying from, or sorry, y is varying from x to 2. So here is y equals x. And y is varying from x to 2. So here is y equals 2. So my region is in here. And x is varying from 0 to 2. So here's my region. Originally, we have the rectangles set for the original integral. The rectangles are set vertically. We want to switch the order, so we set our rectangles horizontally. So we switch the order. For our inner integral, x is going to vary from what to what in this region? We do our rectangle this way. 0 to y. X is going to vary from 0 to y. And x is going to, or sorry, y is going to vary from 0 to 2 in this region. And then we have e to the minus y squared dx dy. Well, e to the minus y squared dx is an easy one to evaluate. What do we get when we evaluate that? This is x times e to the minus y squared, because this is a function of y, it's constant. So we get x e to the minus y squared evaluated on 0 to y, dy. And this is x equals, if it helps you to write this out, x equals, to remember how to substitute this in. So this is x equals. So from x equals 0 to y, when we evaluate this integral, we end up with 0 to 2 y e to the minus y squared dy. That looks a little better, doesn't it? U equals u equals y squared. Du is y dy. So we have e to the minus u du. Actually, do we want u equals y on this one? U equals y squared, right? So then du would be 2y dy. So we have negative 1/2 when we evaluate this integral, e to the minus negative on, oh, there it is. E to the minus y squared evaluated on 0 to 2. And when we evaluate this, we get 1/2 1 minus e to the minus 1/4. So when we switch the order of integration, we change this from basically an impossible integral to one that is pretty easy to do. Negative, let's see, did I do it right? So minus y squared, yes. Negative 4. So we started with an integral that was basically impossible to evaluate, ended up with an integral that's pretty easy to evaluate. So sometimes switching the order of integration makes our integrals possible to do, when otherwise they would not be possible. And on block day, we'll give an interpretation to what this integral is telling us when we have this function inside here that we're evaluating. So we haven't given an interpretation to this. On block day, we will give an interpretation of what this is telling us. This is that what we're doing here is essentially we're finding a volume of a solid. All right, questions. So what we're doing, the homework today is just taking what we did yesterday, evaluating iterated integrals, and now you're going to have to, you're going to have to set them up based on a region. You might have to switch the order of integration to make the integrals easier to evaluate. And on other problems, you're just going to be switching the order of integration in order to practice that process of switching the order of integration. So the important things when you switch the order is always sketch the region and use the region to find your limits of integration. All right, there you go.